Hello, everyone, and welcome to this session for proof complexity. We have, I think, 4 talks. The first one is Adrian She from University of Toronto, and he will be speaking on the algebraic proof complexity of tensor isomorphism. Thank you.
Great, thank you for the introduction. This is a joint work with Nicola Gallesi, Joshua Grochow, and Tony Patassi. So first of all, let's define the tensor isomorphism problem. So what is a tensor? Tensors are fundamental data structures that arise in many different areas of science, engineering, and now in theoretical computer science. So if we let V be a d-dimensional vector space over some field F, then a k-tensor is an element of V, this new vector space, which is V tensored k times. And so after choosing a basis of V tensor k, we may think of a k-tensor as a k-dimensional array where each array element is one of your elements of your field F. And we'll generally focus on the case k equals 3 in this talk. So just as the representation of a linear map is not unique, it depends on the choice of the basis, the representation of tensors as arrays is not unique, again, due to the same issue. And so we have to have a notion of what it means for 2 different arrays of numbers to represent the same tensor. And so this leads us to the definition of tensor isomorphism, which is that 2 k-tensors, t and t prime, are isomorphic if they are related by local change of basis. In other words, there exists invertible matrices x1 up to xk, such that when you apply the tensor product of those matrices to t, you obtain the tensor t prime. And so if this is a bit too abstract, these equations can also be written component-wise. And so if we just expand this equation component-wise, we get this equation for each component of our tensor t. So for concreteness, let's discuss a quick example. So for instance, if we let t and t prime be the following 2 by 2 by 2 tensors, where t is 0, 0, 1 plus 0, 1, 0 plus 1, 0, 0, and t prime is 0, 0, 0 plus 1, 1, 1, then we see that these 2 tensors are not isomorphic, since the tensor rank of t is equal to 3, but the tensor rank of t prime is equal to 2. And one can prove that if 2 tensors are isomorphic, then their tensor rank must be the same. However, in the case of tensors, it's also possible for tensors with the same rank to be non-isomorphic. So which makes this question more subtle than the corresponding than the problem of matrix rank. And so these tensors are actually quite special, since these tensors shown here are special examples of quantum states. And this tensor isomorphism problem has been studied across several areas, including in quantum information theory. So to explain the relationship to quantum information, generally a tensor with 3 components can be thought of as a quantum state that is being shared between 3 parties. So suppose that each party has access to their own part of the quantum state, which is a d-dimensional system, and if the parties can produce the state psi prime, starting from the state psi by local quantum operations and classical communication between the parties of their results, if and only if these 2 tensors are isomorphic in the sense that I just described. And so this notion of local operations and classical communication that has been studied in the physics literature and has been is also a notion that experimentalists care a lot about, is related to this mathematical notion of tensor isomorphism. Next, the tensor isomorphism problem has been studied in cryptography. In a paper by G and others, they explored how to use the hardness of tensor isomorphism as a cryptographic assumption that is post-quantum secure. So in particular, in this paper, they constructed identification schemes and digital signature schemes using this assumption. And they observed in this paper that current algorithmic techniques, such as Grosvenor bases or quantum Fourier sampling, seem to fail at solving large instances of tensor isomorphism problems. Furthermore, in a work of Grochow and Chow, they also investigated reductions between tensor isomorphism and other algebraic problems. So for example, graph isomorphism is a special case of tensor isomorphism. And furthermore, the tensor isomorphism problem is polynomially time equivalent to several problems, such as the group isomorphism problem for P groups, that is groups of prime power order, where the groups are presented by their generating matrices. And this case of group isomorphism is believed to be one of the hardest cases of group isomorphism for which we still do not have polynomial time algorithms. Other algebraic structures that tensor isomorphism is equivalent to include matrix space isometry and conjugacy and Lie algebra isomorphism. Furthermore, we focus on the case of free tensor isomorphism, since they also proved in this work that K tensor isomorphism is polynomially time equivalent to free tensor isomorphism for any constant that's greater than 3. So let's see. So in this same work of Grochow and Chow, they raised an interesting question, which is if proof complexity techniques can be used to study this problem. So in particular, this is quite interesting because in the area of SAT solving, we know that these proof complexity lower bounds tell us what instances of SAT solvers are hard for algorithms like resolution. And so it's natural to study what tensor isomorphism instances, or what instances of these algebraic problems that are hard for algebraic techniques such as Grosvenor bases. And so this, the complexity of these sorts of Grosvenor bases algorithms is captured by a proof system called polynomial calculus that was introduced by Clegg, Edmonds, and Pagliazzo. And so we sort of get a win-win situation here, where if in fact there are low-degree PC proofs for tensor isomorphism, we get better algorithms for solving tensor isomorphism complete problems. And otherwise, if we're able to prove hardness results like degree lower bounds, this gives us some justification that our existing algorithms, such as Grosvenor bases, cannot solve these problems efficiently.
Should we name the other bounds?
Sorry, for which part?
The second bullet from the bottom, it says low degree.
PC
Oh,
proofs.
low degree, yes. So,
Okay.
yes, you're right.
Okay. Yes. Okay. So this is maybe not so new, because in several works the proof complexity of linear algebra has already been studied, and one such example is this work by Soltis and Urquhart that show that the inversion principle, which is the theorem that if you have two matrices satisfying A times B equals the identity, then B times A is equal to the identity. Then an encoding of this principle using Boolean variables is hard for the bounded depth Fourier system. And so in one of our theorems in this work, we observed that the same holds for polynomial calculus using similar techniques. And so it's natural to extend these hardness results about matrices to the more general setting of tensors. And so now I will introduce the PC proof system formally and state our results. So polynomial calculus is a proof system that includes two rules. The first is a linear combination rule, which is that given two polynomials P and Q that are equal to 0, then we know that any linear combination of P and of F and G is equal to 0. Next, we have a multiplication rule, which is that if we are given that a polynomial f is equal to 0, then x times f must be equal to 0 as well. And a PC proof is a sequence of polynomials where each polynomial is either an axiom or derived using one of these PC rules. And so if, starting from a system of equations, f1 equals 0 up to fn equals 0, then we eventually get the polynomial 1 using these rules. Then this shows that the system of equations was unsatisfiable. And the complexity of a PC proof is then measured by the highest degree of a polynomial appearing in this PC proof. So we first take a look at the case of bounded rank tensors and show that actually isomorphism of bounded rank tensors can be tested in polynomial time. In particular, we show that if T and T prime are non-isomorphic tensors of the same rank R, then there exists a degree 2 to the power of order R squared PC proof over an algebraically closed field, or a degree order of R squared proof over a finite field f of q. However, in either case, since these constants are independent of the dimension n, we use existing, this shows that the refutations can be found in polynomial time in n. And so to give you an idea of the proof, this proof uses the so-called inheritance property of tensor rank to reduce the original equations to an equivalent system of equations, and then we apply a result called Sombra's effective Nostalensatz. Next, however, the case of bounded rank tensors is very, very special. So, so our next result is that for general tensors, we get degree lower bounds for the non-isomorphism equations. The main technique that we use in our paper is the framework of low degree PC reductions, as introduced by Buss. And so in the interest of time, I won't define what this means precisely, but if we have two sets of polynomial equations, P and Q, then this notion of low degree PC reductions defined by Buss preserves the degree of the PC proofs. That is, if there is a low degree PC reduction from P to Q and a degree D PC refutation of Q, then we get an order D PC refutation of the original system of equations P. So in particular, we show two different reductions between the tensor isomorphism equations and known lower bounds. So recall that the graph isomorphism problem is a special case of the tensor isomorphism problem. So it's natural then to use existing lower bounds about graph isomorphism to prove new results about tensor isomorphism. So we observed that the following reduction from graph isomorphism actually not just gives a reduction between the two problems, but also a low degree PC reduction. So the first reduction is due to Petrank and Roth that reduces graph isomorphism to monomial coequivalence, where monomial coequivalence is the problem of given two matrices C and C prime, is there a invertible matrix X and an invertible and monomial matrix Y such that X, C, Y transpose equals C prime. And in particular, a monomial matrix is a matrix that can be decomposed as the product of a diagonal and a permutation matrix. Secondly, this is combined with Grochow and Chow's reduction from monomial coequivalence to tensor isomorphism. And so we have a lower bound on equations for graph isomorphism due to Burkholz and Grohe that show that maximal degree is required, degree n is required to refute the graph isomorphism equations. So combining their result together with these PC reductions yields an order n lower bound for instances of n by n tensor isomorphism. However, this reduction provides a lower bound for a very particular kind of tensor. That is, the tensors that we get by this reduction are very sparse. And in particular, almost all of their non-zero entries are concentrated on one slice of the tensor. So maybe this is not so desirable from the perspective of tensors. So we really want a lower bound for tensors that are not necessarily sparse. And so to solve this problem, we present a second reduction using the free XOR problem that I think Bruno talked about earlier today. And so a random free XOR instance is with n variables and m clauses is obtained by choosing uniformly at random m clauses from the set of all possible parity constraints. And so we encode each parity constraint as a product of free variables equal to plus or minus 1. And we have Boolean axioms for each variable. And so by the probabilistic method, it's well known that when the number of clauses is sufficiently large, then such a free XOR instance is unsatisfiable. And furthermore, due to Ben-Sasson and Pagliazzo, they proved that over any field of characteristic not equal to 2, then such instances require maximal degree or degree n degree n to refute in polynomial calculus with high probability. And so to describe our reduction from free XOR, given equations at xi, xk equals plus or minus 1, we define tensors by setting t ijk in position ijk to be equal to 1, and t prime in that same position to be equal plus or minus 1, depending on the original equation. And we observe that the free XOR equations are satisfied if and only if t and t prime satisfy the following equation, where A is a diagonal matrix with plus or minus 1 entries. And so in general, we call this problem, this special case of tensor isomorphism, where now the matrices in each factor are the same, to be, this problem is called cubic form equivalence. And we say that they're X equivalent if the constraint X must be satisfied for an isomorphism to hold. And so we present a series of reductions from free XOR to tensor isomorphism that can be implemented in low degree PC. So we just observed that the free XOR problem is exactly the same as equivalence of cubic forms restricted to plus and minus 1 diagonal matrices. And so in our first step of our proof, we remove the diagonal restriction to change that to the restriction of monomial matrices. And this can be done by ensuring that the underlying hypergraph of the free XOR instance has no non-trivial automorphisms, and this is guaranteed at sufficiently large clause density. Next, we remove the restriction of being a plus or minus 1 monomial matrix. And this is done by designing an appropriate gadget that enforces this new constraint. And we show that this gadget reduction gives us in fact a low degree PC reduction as well. So next natural step is to remove the monomial constraint and change this to a constraint for general invertible matrices. And again, this is done by a gadget type reduction and showing that this gadget also gives you a low degree PC reduction. Finally, we remove the constraint that the free matrices have to be the same to obtain a general instance of tensor isomorphism. And we observe that a reduction due to Fortner, Grochow, and Severchuk from cubic form equivalence to tensor isomorphism actually gives you a low degree PC reduction as well. And so, putting all these steps together gives us an n to the 1/4 lower bound for tensor isomorphism on n by n tensors. Although this is polynomially weaker than the previous lower bound, our tensors no longer need to be sparse in the sense that the non-zero entries are now sort of evenly distributed or randomly distributed across the slices of the tensor. So which is quite nice from the tensor for these instances of tensor isomorphism. And so, how much time do I have left?
5 minutes,
Okay.
not including questions.
Okay. So in summary, we study the complexity of tensor isomorphism, which is a central problem in theoretical computer science and quantum information, using these techniques in proof complexity. We construct our hard instances of tensor isomorphism for polynomial calculus, and we in fact observe that many of our reductions also go through in the stronger sums of squares proof system. This is because their random free XOR is not only hard for polynomial calculus, but is also hard for sum of squares. And furthermore, we observe that tensor isomorphism for the special case of bounded rank tensors can be done in polynomial time. So in terms of, we believe that there's still a lot of open questions in this area. For instance, one of the things that we do is to introduce a proof system called a PC plus inversion that enables a PC to perform some linear algebraic reasoning. So, and recall that from that inversion is the matrix inversion principle that A times B equals identity implies B times A equals A identity. And so we observe that, this requires high degree in PC, but, what if we add it as an axiom schema in this new proof system? So, in particular, isomorphism of matrices, or equivalently determining if two matrices have the same rank, can be done in constant degree in this new proof system. However, we expect that there should be some hard tautologies or hard systems of polynomial equations for this proof system. And so we leave it as an open question to prove any lower bound in this extended proof system where now PC can do some linear algebra. And in particular, we conjecture that isomorphism of free tensors does require high degree in PC plus inversion. And this would sort of capture the intuition that linear algebra alone or matrix algebra alone isn't enough to capture the complexity of tensors. Next, we leave open the correct value for the PC degree of rank R tensor isomorphism. Our constructions give a lower bound of R to the quarter, and our upper bounds give a bound of R to the power of 4 over a finite field, and a bound that's exponential in R over an algebraically closed field. So this is quite a wide gap, especially in the case where we're working over an algebraically closed field. Next, we're interested in size bounds for tensor isomorphism. Since usually if we prove a degree lower bound, that implies a size lower bound, but only in the case where your variables are Boolean valued. And this is not the case for the tensor isomorphism equations we consider. Finally, Grocha and Chow also present some other reductions between graph isomorphism and tensor isomorphism, and we've only used one of the reductions that they present in their original paper. So it's an open question to ask if some of these other reductions that they present are also low-degree PC reductions. Thank you for your attention.
PC plus inversion. So how do you encode this inversion principle? You have there an implication.
We encode it as a derivation rule. So it's a new derivation rule that we add in PC.
Right. So it's not a scheme. It's not an axiom. It's just a rule.
Right.
Can you go over which field is it?
Over any field. I guess the same field as the original system of equations.
Can you just go back and explain how do you encode the tensor? It's like 10 slides, I think.
Okay. Which slide?
Just go back. I'll tell you where to start.
Here?
Yeah.
Or?
No, before you show the lower bound. Yes, this one. No, the one before. Yeah, so what is, how do you encode this TIJK code 1? So these are just variables?
No, so these are the tensors that we're defining.
Yeah,
So
okay, so can you,
so the variables are the matrices that give you the isomorphism.
no, the previous slide had this statement.
This one?
Oh, no, this one. Oh. Yeah, so, no, it was, yeah, this one, this one.
Okay.
So how do you encode it as in variables, right? As a tensor, and how do you do the reduction? I mean, it's
Okay, so I guess maybe I should write it down.
well, it's too long. Then,
So now, so the variables are, just put like x1 up to xn on the diagonal, and if we know that xi, xj, xk is equal to plus or minus the identity, then we put 1 in entry ijk of one tensor, and the right-hand side of ijk equals whatever this is, and then well, this system of equations.
so A is a specific one. It's not.
Right.
Specific, oh, I see. Yeah.
Right, and this system of equations is identical to the original
Right.
instance that we get.
Oh, okay.
Sorry, does that make sense now?
Yeah, thanks. Thank you.
Okay.
So let's thank Andrew. Oh, we have a question.
Oh, just a small question. How do you compare like PC plus the linear algebra action with some other system like SOS?
That's a good question. I don't think we have a candidate to compare the two yet.
Oh, okay.
Yeah. So I think it's an interesting open question to see if the inversion principle can be refuted in low degree SOS.
Oh, okay.
Since our reduction uses the pigeonhole principle, but we know that that's easy for SOS.
But what about like the other way around? Like can you simulate SOS by the inversion principle?
I don't know,
Thanks.
but I think it's a good question.